for experimental purpose, mostly on the high-speed QKD. For speakers, for each talk consists of 10 minutes, 6 minutes for speaker, and 4 minutes for Q&A. In the audience, if the audience have any question, please type your question in the Q&A box on the Zoom or by raising your hand and being unmuted by the session chair, or ask a question directly in the on-site. Okay, our first speaker is the Fabi Gralenfelder on the topic of towards 100 megabits per second secret key rate QKD. Fabi, please.
Thank you. So let me quickly share my screen. Okay, I hope you can see it. Is it okay?
Yep.
Okay, then. Hello and welcome to my short teaser talk here. So my name is Fadri Grünenfelder. I'm from the University of Geneva in Switzerland. I'm working in the Quantum Technologies group as a PhD student. And today I'm going to talk to you about how to reach high secret key rates with a QKD system. So why do we want to have high secret key rates? I mean, a famous example is video conferencing, as we do it right now. So if you want to have a high definition video conference, then it's recommended to have a bandwidth of 6 megabits per second or even higher. And if you want to encode or encrypt this video conference with the one-time pad, then obviously you also need a secret key rate which is as high. And obviously there are other applications which can benefit from a high bandwidth, for example cloud storage or distributed computing. And in general, any encrypted communication, I guess, can benefit from an increased bandwidth. So the protocol we are using in our setup is the simplified time-bin BB84, as shown here. And obviously a key ingredient for a high secret key rate is a transmitter which can generate states at a high rate. So here we have Alice, which generates pulses at 2.5 gigahertz. And with a Michelson interferometer, which is unbalanced, you can fill up 2 time bins, and then you can encode the states with an intensity modulator. And the states are shown here. You can see for the key generation basis, the set basis sends either an early pulse or a late pulse, and for the monitoring basis, just a superposition. Additionally, we use the decoy state protocol, so we have one intensity for the signal and one for the decoy. On Bob's side, we bias the basis choice highly towards the set basis. So we need a very good and very fast detector there. And so we use a multi-pixel SNSPD with 14 pixels. And in the X basis, we also use a multi-pixel SNSPD, but it has only 4 pixels because the detection rates there are much lower. So if you look at such a setup, here we can see the multi-pixel detector fiber coming in, and if you look at the schematics, it would look something like this. And actually the active area is only this black dot here, so if we zoom in, it looks like this. So these are the nanowires, and as I already mentioned, we have 14 pixels, they're interleaved. This means that all the pixels receive about the same amount of light, and they're short, which helps with jitter and recovery time. And we measure at 1 megacount per second, 79% efficiency, and a jitter below 24 picoseconds. These are all very good values, but the question is now, can we have a good jitter and a high efficiency also at a rate above 300 megacounts per second, as is required for the experiment we want to perform? And so for this, we improved a lot on the detection electronics of the SNSPD, as you can see in my long talk. And in the end, we obtained results like this. So we have the count rate versus the system detection efficiency, and we can see that we start with our high efficiency, but then at some point the efficiency starts to drop, and this orange X is actually the count rate we would like to have for our experiment. So it's 320 megacounts per second, but still we have an efficiency of 60% and a jitter which is 47 picoseconds. And in the X basis, it's not so drastic because the count rates are much lower. So the efficiency actually doesn't really change too much compared to the best efficiency we can have. We have a jitter of 55 picoseconds. And in our experiment, we also perform real-time post-processing. So we have a LDPC error correction code, low density parity check. And this low density parity check operates with a syndrome size of 1/6, which requires a very low QBER below 0.5%. But as you will see later, we can achieve this with our system. And we implement the LDPC in a separate FPGA on Alice side and achieve a throughput above 200 megabits per second, which is well enough for our experiment. We also perform privacy amplification in real time. This we do on a GPU, on a commercial one. It has a throughput of 3.5 gigabit per second, which is obviously well above what we are actually needing. And we can do this on a block size of about 10 to the 8 bits. So now what do we achieve with our system? So at a long distance, relatively long distance of 102 kilometers, we achieve a QBER in the set base of 0.3%, which is really low, and a phase error rate of 1%. And this gives us a sifted key rate of 7.8 megabit per second and a secret key rate of 3 megabit per second. And then the more interesting part is what can we do over a short distance, where the detectors are really at the limit in terms of count rate. And here we achieve a QBER set, which is basically unchanged, a little bit higher because of the jitter of 0.4, and the phase error rate, which is a bit lower because of the reduced dark count contribution of 0.8%. And the sifted key rate is almost 60 megabits per second, and we achieve a secret key rate which is 63.6 megabit per second. So with this, let me conclude. We can show that we have high-performant multi-pixel SNSPDs with a very low jitter and a very good efficiency at the same time, and at a count rate of 320 megacounts per second. Additionally, we have record-breaking secret key rates, 63.6 megabits per second over 10 kilometers and 3 megabits per second over 102 kilometers of fiber. And with this, I want to thank my team working with me on this experiment, and you as the audience for listening to my talk. Thanks.
Okay, thank you very much. And we have already got one question from the Q&A room. It's from the quantum hacker Vadim Makarov. Is this going to be commercialized?
Not that I know of. I mean, there is this company in Geneva, ID Contig, who worked with us on this project as well. But the main part or the main contribution from their side was actually the detector. So the members of the detectors team, they actually, some of them work in ID Contig. And so the detector was produced in collaboration with ID Contig. But the QKD part was fully done at the University of Geneva. So probably it won't be commercialized, at least the QKD part, and at least not in this form.
Okay, thank you. We have a second question from GoCal. The question is, any reason why only 10% of the signal is attenuated? See slide number 3.
I mean, mainly there we only use, so the splitter here is just used for power monitoring, and the rest goes to Bob. And the reason why we only took 10% is just that we need less attenuation on the variable attenuator, because usually sometimes we even need 2 variable attenuators here if we don't have only this 10%. So it's better to just use a low power on this quantum channel arm. So it's more a practical reason.
Very clear. So any further question from audience? So if not, I think I'll take liberty to ask one question. So right now, your title is towards 100 megabits per second, 6-bit key rate. you have achieved 65 megabits per second, which is fantastic. I assume right now you use 2.5 gigahertz clock rate. I assume from your detector time jitter, there's a further room to improve the clock rate to achieve the target. So when do you think we can see the 100 megabits per second?
So we use this system because I mean it was already very well tested. So I mean we already used this in different experiments, and we mainly used it because we know that we can have a really low QBER, which is important to not lose too much bits in the error correction. We did some tests in our group also with the polarization-based setup at 5 gigahertz, but there the QBER was much higher. I think if I remember correctly, it was in the order of 1.5 to 2%. And with this low density parity check error correction, we would lose much more bits. So this is basically one of the main reasons why we use this system and not a system at 5 gigahertz.
All right, thank you very much. So actually, there's one more question asking, presumably we can answer offline. Due to time limit, let's move to the next talk. The next talk is by Rebecca Sachs on the high-speed integrated QKD system. Please.
Hello, everybody. I'm Rebecca Sachs, a PhD student at the University of Geneva in the group of Hugo Spinden. So today I'll give a brief overview of our high-speed integrated quantum key distribution system. So this has been done in collaboration with the Politecnico in Milano, as well as the Institute of Photonics and Nanotechnology in Milano, IDE-Quantique in Geneva, and Sequoia in Berlin. So in the spirit of further developing QKD and eventually industrializing QKD, a very natural step is to go towards integrated platforms. There are many advantages of this. For example, we can see lower costs and scalability. So here for our integrated QKD system, we use the 3-state time-bend BB84 protocol with one decoy state, the one that Fadri just presented. At a repetition rate of 2.5 gigahertz and 1550 nanometers. So just an overview of our setups. We have a laser, external laser, integrated, and the rest of our transmitter is integrated. Quantum channel integrated receiver and off-chip single photon detectors. Alice and Bob are connected via service channel and controlled with FPGAs, such that we can do a real-time secret key exchange. And for this, we use the cascade error correction algorithm. So first, for some details on the transmitter. So it's based on silicon photonics, and the optical part has a footprint of around 1.1 times 4.5 millimeters squared. So it's this part here. Light is coupled in via a grating coupler. And on the other small rectangle you can see here is the electronic integrated circuit, also in silicon photonics. So some comments on the choice of platform. So using silicon photonics, we can have a very small footprint. We can also integrate not only the photonics, but also the electronics, obviously. And so for our purpose, this was quite nice. We could have digital to analog converters used to use for intensity modulator and optics on chip. Also for fast modulation. However, we cannot easily integrate a laser using silicon photonics. That would be a disadvantage. Overview of the schematic of the optical part. So we can enter via one of two. We have one of two choices, either through a ring filter or not. Then we go to our imbalanced interferometer. So as Fadri said, here we have a delay line of 200 picoseconds. Our qubits then pass through an intensity modulator where we can modulate the 6 states needed. And then we have a variable attenuator to attenuate down to single photon 11, and we go out with the chip. Now for the receiver. So here's a schematic again of the receiver. So we enter the chip, and we have here a 9010 beam splitter. So 90% of the light will go towards the Z basis detector. So detections here will be used for the secret key. And the other 10% will go through, will come to the monitoring detector, to the X bases, where here we have an identical imbalanced interferometer as for the one of Alice, about 200 picosecond delay line. So here's a photo of the chip. And the receiver is based on silica and is fabricated in Milano in the group of Roberto Salame using a femtosecond laser micromachining technique. Again, some comments on the choice of platform. So here we have very low losses, so around 3 dB. So this includes propagation and coupling losses. So in both bases, we have 3 dB. And additionally, it's polarization insensitive. So this means that the entrance beam splitter, as well as the visibility of the imbalanced interferometer is independent of the polarization. This is something that's quite hard to achieve in integrated circuits due to the intrinsic birefringence. And so this is something that the group of Roberto Salame could worked on, and they managed to control this birefringence. Okay, so however here we cannot, again, integrate a detector, and we have a relatively large footprint compared to silicon photonics. So for the disadvantages. So again, for the full results, so the experimental setup I showed you, so we use either, in terms of the single photon detectors, we use either superconducting nanowave single photon detectors, SNSPs at 0.8 Kelvin. So this is more for a system characterization, a check of performance. We don't really want to have, since we have to cool them down to cryogenic temperatures, this doesn't go very much hand in hand with the use of practicality of integrated photonics and integrated QKD. So for the rest of our results, we used indium gallium arsenide, indium phosphide, single photon avalanche photodiodes at around -85 degrees Celsius. So they're a bit more, say, mature for real world implementation. So just for this short talk, I present two of the results, one for each of these. So for the SNSPD detectors at an emulated distance of 40 dB, so we attenuate using actually the integrated chip. We achieve a relatively high raw key rate, low Kuber and phase error rate, and get a good secret key rate. So this corresponds well to the results we obtained with our fiber-based setup. And similarly, using the InGaAs at now, I chose here at 30 dB, we achieve a lower raw key rate. This is normal. We have a lower efficiency as well as a higher jitter and higher after pulsing probability. But we still get results very similar to our fiber-based setup. So this is we're quite happy with. Yeah. So with that, I would like to thank all the collaborators and the team in Geneva, as well as you for your attention.
Okay, thank you very much. So while we waiting for the question from audience, I will start with one question first. So how do you compare your current system with the system used by the previous speaker in your group?
Okay, so there are quite maybe some differences. So maybe I can show you just I think I have here in the backup a photo. This is our fiber-based system, but not exactly the one that Fadri Grunenfelder showed. So in Fadri's setup, this was to go towards high speed. And so he did a slight modifications of the setup. So for example, the splitter in Bob is 99.1%, whereas in my case, it's at 90-10. So the goal here wasn't to go towards high speed. So this is one of the differences. Also, in terms of detectors, we don't use at all the same techniques. We use a different SNSPD, yeah, I use InGaAs and SPDs, but not the same as Fadri, who uses multi-pixel. Yeah. Is that answering your question, or the other?
Oh yeah, perfectly clear. Thank you. Yeah.
Oh, and then obviously, okay, my setup is integrated, and this is not. But yeah. Otherwise, the performance is quite similar.
Okay, perfect. Questions from audience? Okay, looks like it. Yeah, we have one question from Andreas Pope. question is, did you need to implement a very stable temperature controller for your chips at Alice and Bob?
Yeah, so Bob is temperature stabilized and Alice. So for Bob, for example, to control this by refringence, we have to set it at a specific temperature. This is quite sensitive, but we managed to stabilize it without much of a problem. And for Alice, we stabilize it more such that the phase of the interferometer wouldn't fluctuate. But again, this is not a big problem in our setup, but we stabilize both. Yeah.
Okay, thank you. Any further questions from audience? Okay, if not, I think your talk is perfectly clear. Let's move to the next talk. The title is Fully Integrated High Key Rate Wavelength Division Multiplex Multi-Channel QKD. The speaker is Fabian Beutel. Please.
Yeah, thank you for the introduction. My name is Fabian Beutel. I'm from Münster University and recently also from Pixel Photonics, where we built actually waveguide integrated single photon detectors based on superconducting nanowires. And we already heard two talks about high key rate, QKD, and we actually think that when we talk about how to increase the secret key rate further, wavelength division multiplexing is a very attractive option. This is not only because it is also used in classical communications, but also because it's conceptually relatively simple. And as an example, so we depict a time bin protocol here. I think it's actually very similar to the one that the previous speakers used, but can also be the coherent one-way protocol. And if you want to multiplex this on the sender side, things are especially simple because essentially you can just replicate the different encoding components a few times on different wavelengths. You don't even need a multiplexer because typically you have enough signal power available and you can just combine the signals using beam splitters since you don't really care about the loss at this point. And also on the receiver side, you don't need to replicate all the components, but you can actually share some components for different wavelength channels, such as, for instance, the delay line interferometer can be shared among multiple wavelength channels. And then, of course, here you do need a demultiplexer, one for the X and one for the Z bases, and then you need the single photon detectors for each of the wavelength channels. Of course, conceptually it's simple, but if you want to implement this experimentally, you will have some trouble if you use bulk components, and this will become very messy very quickly with high channel numbers. But if you use integrated photonic circuits, this is actually not too much of an issue anymore, as these implementations typically scale extremely well with the channel number and also in a very cost-effective way. So this is our goal today, and for our work we focus on the receiver side. And so our goal is to basically end up with a chip which has one input fiber and electrical outputs, and all the photonics is, including the single photon detectors, should be integrated on a single chip. So it's really a robust system. For this, of course, we need to implement the demultiplexer also on chip. And for this, we use ring resonators in an add-drop configuration. And this works by having waveguides and this resonance structure. And typically, if you insert light here, then the light will mostly pass through, but if you hit the resonance wavelength, then it will actually be diverted to the drop port here. You end up with a nice filter, and the filter characteristics can be greatly improved by cascading multiple rings together, and you end up with a very flat top filter shape and a very good extinction ratio. This configuration also has an additional benefit, and that is that it is symmetric. So you can not only insert light here from the input, but also from the throughput side. You can in principle insert light, and if it's resonant, it will actually be diverted to the fourth output, basically. And this means that the two demultiplexers that we conceptually need to implement in our receiver can actually share the same physical structure. So for the X basis, we can insert light from the right, and for the Z basis from the left. And this ensures that we don't have any misalignment between the X and the Z bases. We only need one physical demultiplexer on our chip, and this makes a lot of things much easier. So our chip is based on the silicon nitride platform. This is what it looks like under the microscope. It's roughly 1 by 1 millimeter, a little bit smaller actually in the Y direction. And we do have one input coupler. The others are all just for calibration purposes. So we have one input coupler, which is a efficient fiber-to-chip coupler. And most of the light for the Z bases then is actually diverted directly towards the different ring resonators, which are a little bit shifted so that you end up with 4 wavelength channels, and then goes on to the detector. Whereas part of the light, about 10 to 15%, is diverted into the delay line interferometer, which we also realize on chip, and then enters the resonators from the other side. We use waveguide integrated single photon detectors for detecting the single photon. So this chip sits inside a cryostat, which means you don't need any active temperature stabilization anymore. The interferometer is actually super stable because it's cooled down to about 2 Kelvin anyways. And these are actually also have the nice benefit that they are quite fast. If you look at the characteristics, so we sweep the wavelength with a laser signal that we send into our chip and see that we can achieve about 15% system detection efficiency. And this includes all the components on the chip, including also the basis selection splitter and such. It's not heavily optimized here. Our measurement setup needs to be flexible so that we can measure many devices, but in principle, system detection efficiencies of about 80% or even a little bit higher are realistic with these devices if you really optimize the fiber-to-chip coupling further. And you can see, so the solid lines is the Z bases, and here below the light lines are the X bases. And if you zoom in here, you can actually see on the right side the interferometer at work, and this actually yields visibility across all the 4 wavelength channels of about 98%. We also performed a QKD transmission with this receiver chip. We use bulk components on the sender side, but this is all measured with the one chip I showed you before. And in total, we actually achieve more than 17 megabits per second at 3 dB channel attenuation. So this is a little bit more than 10 kilometers of fiber. And at 10 dB, we still have about 12 megabits per second. So this means we do see some saturation here towards the lower end, but without using any multi-pixel detectors for each channel, we don't really see strong saturation because the dead time of the detectors that we use, the waveguide integrated detectors, is typically very low. When we look at the error rate, this is, so what you can see in the solid lines here, which is the Cuber, is that it doesn't strongly, or mostly it doesn't depend on the channel attenuation. And what this tells us is that the detectors and the receiver chip, the noise there really isn't an issue, but the Cuber is mainly caused by the sender side, which is not fully optimized yet. So the dark counts and also the jitter don't really play a major role for our implementation as they are so small. The phase error rate goes up a little bit towards the end because there the count rates typically are much lower, and then at some point you do have to take the dark counts into account. Finally, we also tested for crosstalk between the wavelength channels. And for instance, if you measure at channel 3 and send in a different signal at channel 4, we see a maximum error contribution of about 0.2%. So the error goes up by at maximum 0.2%. And for the results that we achieved, this turned out to be actually almost negligible. So here this channel separation works very well in this chip and can also be scaled up to higher channel numbers in principle. Yeah, with this, I would like to thank you for your attention, and happy to answer any questions.
Okay, thank you very much. So, any question from the audience? So, I'll ask the first question. You use a silicon nitride platform.
Yeah.
So, what's the transmission loss of your chip?
So within the spiral, we measure roughly 0.4 dB per centimeter. So we use some optimizations such as annealing and also a cladding structure. This can be greatly reduced further, but for our purposes, it's more or less sufficient. So the loss is roughly 0.4 dB per centimeter.
So what about the coupling loss?
Fiber to chip coupling, you mean?
Yeah.
In this case, as I said, the loss was a little bit higher, so it was probably around 3 dB, which is caused by the larger distance between the chip and the fiber. But we've previously demonstrated, I think in a different paper, that we can actually achieve system detection efficiencies efficiencies of almost 80% using these three-dimensional couplers together in combination with the single photon detectors that we use here. So in principle, once you optimize the setup, the measurement setup, you can actually achieve quite high system efficiencies.
So we have 2 more questions from the audience. The first question is, what limits the number of channels to 4?
In our case, it was mostly practical because then you have 8 electrical outputs, and currently our cryostat only has 8 RF channels. But this is something that we also actively work on. So in a different project, we actually implemented a 64-channel SNSPD system, where probably we will extend this further. A second limitation is the FSR of the ring resonators. So at some point, they are, of course, the spectrum repeats itself, so you have the free spectral range. But there we actually also have developed an approach to overcome this limitation. There are different approaches. You can also cascade rings of different sizes to overcome the FSR limitation. Currently, this is a limitation for us, but we also basically are working on a solution here. So in principle, I think you can really cover a high number of like 50 channels.
Okay, thank you. We have last question from audience from Haikon Lo. What is the long-term stability of your system?
It is actually quite stable. So I don't think I have the plot here, but we did perform I think 24 or 12-hour measurement, and basically since the temperature stabilization in the cryostat works or is relatively stable, and the silicon nitride is also not very sensitive at low temperatures to thermal variations, we actually didn't see a major decrease in performance over a measurement at 12 or 24 hours. I don't remember at this point, but so over multiple hours, it's actually very stable due to the low temperature that we work on.
Okay, thank you. So now let's move. Let's move to the last talk by François Rumestin. The title is Experimental Demonstration of Discrete Modulation Formats for Continuous Variable QKD.
Hello, Zilian. This is
Eleni. Sorry, yes.
I'm giving the talk on behalf of François, who has finished his PhD and could not become available for this presentation. So let me share my screen with the talk. Is it okay? Can you see the full screen?
Yeah.
Yeah, okay. Thank you very much. So I'm Eleni Diamanti from Sorbonne University. So I'm going to be talking to you today about the experimental demonstration of discrete modulation formats for continuous variable QKD. So we're going to switch a little bit to the continuous variable framework for this talk. So this is joint work with Nokia Bell Labs, where François did his PhD together with our lab and our colleagues. So let me go straight into the description of our protocol. So in continuous variable QKD with coherent states, what we're doing is that we're generating a constellation of coherent states that are characterized as usual in CV-QKD with their amplitude, their phase, or by their quadratures. And then these are picked, and they are also characterized by a fundamental shot noise or vacuum fluctuation. So whatever noise is beyond this shot noise is called an excess noise, and this is a very important parameter in continuous variable QKD. So these states are then picked randomly from a constellation that is defined by the modulation format that is being implemented by Alice, and then she adjusts the power which defines the variance of this modulation. These states are then sent over to the quantum channel, which is characterized by the transmission efficiency and this excess noise we talked about, and then they are measured. They are mixed, the states, with a local oscillator or phase reference signal, and they are detected by coherent detection techniques, which can be either single quadrature measurements or double quadrature measurements that have become known in the field as homodyne or heterodyne detection, respectively. So now Alice and Bob are performing noise variance measurements that are, all these parameters are linked with this equation that you see here. And in our work, we're working in this trusted or calibrated noise scenario, where the two parameters that are characterizing the detectors, so the quantum efficiency and the electronic noise, are considered well calibrated and therefore trusted, and they cannot be used by you. So this quantum transmission part of the protocol is followed then by the typical classical post-processing, which includes parameter estimation, error correction, and privacy amplification. So let's move on now to the modulation format, which was the major focus of this work. So typically in CV-QKD, we have been using Gaussian modulations, which have the good property of leading to very strong and simple security proofs, where one can use assumptions on Gaussian modulation distribution, and they have led also to very good, excellent experimental results. But Gaussian modulation is actually not used in industry of telecom optical communications, as because of the limits in the bandwidth modulation, in the bandwidth of the modulation, it cannot be perfectly implemented. So in the last year, it has become common to look at discrete modulation formats, like, for example, the 4-stage one going to the other extreme, which is a quadrature phase shift keying, where there are several security proofs that have come forward. It does lead to Asian implementation, but actually the performance is quite lower. And so what we have done is this work, we have considered intermediate modulation formats called probabilistic constellation shaping QAMs that are described by discretized probability distributions that you see here, and we have examined how they perform experimentally for CV-QKD. The very first thing that one needs to do is, of course, to adapt the security proof, because one cannot use anymore the assumptions that are done for Gaussian modulations. And this was done very recently by our colleagues from India, Anthony Leverrier and his colleagues, where they have performed an analytical proof providing explicit asymptotic secret key rate for any arbitrary discrete modulation. So this essentially covers the probabilistic constellation shaping QAMs that we have used in our work. So what we have done is we have adapted this proof for a realistic receiver, because this was not included in this proof. And we have also done an ad hoc analysis of finite size. Remember that this proof is for an asymptotic secret key rate, and in real experiments, we need to take into account finite size effects. So what we have done is we have considered the worst case estimators for the relevant parameters from the security proof. And you see here from this analysis that for reasonably intermediate sized QAMs, one can get almost optimal secret key rates for an optimized range of modulation variance values. So this is the experimental setup. So we have used an 10 kilohertz lasers, an IQ dual polarization modulator to generate a 600 megabaud signal. Two types of experiments have been performed with optical fibers that are either 10 kilometer, almost 10 kilometer standard SMF, or a 25 kilometer low loss fiber with a somewhat lower coefficient. We have used an optical switch for the noise calibration, for short noise calibration, and the so-called heterodyne or double quadrature measurement based on amplified balanced photodiodes. And the measurements were taken with a digital oscilloscope. A couple of things to note. So these CW pulse shaping techniques use optimally the spectrum, but they do require digital signal processing for the signal recovery using pilots. We have used a local oscillator, which puts constraints in the laser language. And of course, these commercial balanced photodiodes need to be short noise limited and high bandwidth. Digital signal processing, I won't have to go the time to go into the details, but they follow standard protocols that have been developed with high performance by the Nokia Bell Labs team. We're using time multiplexed pilots, QPSK pilots that are 50% of the signal and are 14 dB higher than the QKD symbols. And the crucial point in the experiment was to calibrate the noise and optimize all the DSP parameters and the pilot piper to minimize this excess noise. These are the experimental results we have obtained with the system over 92 megabits per second over the 10 kilometer fibers. These are record high secret key rates and then 24 megabit per second over the 25-kilometer lower piper. You see here the stability of the system over the PCS. You will also notice that there were no key was possible on the 64 QAM for the 25-kilometer. And indeed, if you look at the dependence of the secret key rate as a function of the attenuation or distance, you will see that these results are adapted to very high secret key rate at metropolitan scale distances. You can find more details on this work in this preprint with a number here. So this brings me to the conclusion of this presentation. Let me focus mostly on the future work. So of course, on the theoretical side, there is a need for full security proof with finite size effects. We're also optimizing the system, the DSP, homemade DSP as well in our lab in Paris. We're working on extending the distance, making the baud rate even higher, implement a coexistence with classical signal, implementation of data reconciliation, deployment over real on-field fibers. And in particular, we're also working on photonic integration and compatibility with satellite communication systems. And this is what will be presented by posters. I invite you to look at our work on the posters will be presented on the Wednesday session by Joan Pietri, Valentina Marulanda Costa. And thank you very much for your attention.
Thank you for your talk, Eleni. I'll ask first question. So in your one slide, you show that the scale key rate is kept by to 0.1 bit per symbol for 256 QAM. Is this bit rate is a fundamental cap or due to the release like a device imperfection? Sorry, earlier.
Can you repeat the question, Zillian? Sorry, I'm not completely sure I understood.
So in one calculation curve, simulation curve, you show the bit rate, yeah, this one. The secret fraction is 0.1 bit per symbol. Is this a fundamental limit or due to some imperfection?
Look, in this simulation curve that you see here, it has come out of the security proof that is shown in this with a very detailed security proof with specific correlation coefficients, and these are the three parameters that are extremely important in this proof. And it also includes these curves that you see here, specific numbers for a receiver. Okay, so I wouldn't call it a fundamental limit. It's a kind of a practical secret fraction that you see here in bit per symbol for these key rates and adapted to a receiver asymptotic secret rate. But I would say it comes close to what you can expect in practice. I think from a fundamental point of view, you could potentially get it a little bit higher than this, but not much. This is what I would think.
Okay, well, thank you. We have one question from audience, from Kevin Jack. How did you adapt the security proof for a trust detection scenario, find out such effects? I remember that the security proof in the Dennis et al. Paper are asymptotic without a trust receiver.
Yes. Absolutely. So I confirm this, and this is exactly what is written in this slide. So the actual security proof is for asymptotic key rates and without receiver, and this is why we have adapted this. And I invite you to look at all the details in the paper. And the references therein, because they have not been published yet. So this is except for this preprint and the PhD also thesis of Francois, where we have detailed we have written in many details this the inclusion of the finite size statistical effects, the way that we have calculated these worst case estimators related to the security proof parameters, which are not the usual parameters that have been used up till now. Up till now, it was the transmission efficiency in the excess noise at Bob's side, while this proof introduces new coefficients, and we have calculated the worst case estimators. This essentially means that you calculate what is the worst case that you can possibly get during the parameter estimation phase of the protocol, compatible with your experimental data. So this is a technique that we have been using for other implementation for some years now for our experiments, that in the absence of an actual formal proof include taking into account finite size effects. Having said that, I do expect that that these numbers will not change a lot. I'm quite confident on the security of the implementation based on these worst case estimators. We have discussed this in length with my colleague Anthony Revelier from INRIA, and although we're very much looking forward to a formal proof of this type of techniques typically come close to what can be expected in practice. As far as the receiver is concerned, including the quantum efficiency and the electronic noise was straightforward. So this is quite straightforward to include in the proof.
Okay, thank you. Looks like no further questions from audience. Okay, let's conclude this session by thanking all the speakers. Thank you. Good.